In this video, I'd like to use the tools we have so far to reason out what the electric field strength must be like in the vicinity of a uniformly charged sphere. So what are two possibilities for a uniformly charged sphere? Well, one possibility is that the charges reside on the surface of the sphere, but not on the inside of it. This would be a sphere of uniform surface charge. But we could also have a sphere of uniform charge density, and that's a little different. In that case, the charge is distributed uniformly throughout the sphere's entire volume, and it would be inside the sphere. Let's do an analysis of both situations. We're going to have an axis for each, and compare it to a familiar situation from the past, a point charge. A point charge has no volume. And we said before that the field around a point charge would be kq over r squared. So the field decays as we move away from the point charge, and it heads toward infinity as we get close to the point charge. So what does the electric field do for these other cases? Well, Gauss's law can be used to determine that answer. In Gauss's law, we have to choose a Gaussian surface with which to analyze our situation. So let's pick a Gaussian surface here that is just outside of the boundary of the sphere. And we could do it for both. Let's say that our sphere has a radius a in both cases. According to Gauss's law, the electric flux will be equal to the charge enclosed divided by epsilon naught. And let's say that our uniform sphere has a total charge of big Q on it. We call it Q total. And that's going to be the same for both. It's just that in one case it's only on the surface, and in another case it's distributed. Hopefully it's clear that the electric flux here for both is going to be equal, because the charge enclosed in both cases is Q total. And if our point charge had a value of Q, and let's say we made one of these Gaussian surfaces around it, we would see that all the Gaussian surfaces enclose the same amount of charge. And they would have the same formulas in all cases. So what does this tell us about the electric field at the boundary of our Gaussian surface? Well, we have to replace the electric flux with electric field times area. The area of all our Gaussian spheres is going to be the same. Our surface area will be given by A equals 4 pi r squared, but in this case we said that the sphere had a radius of A, so I'll use that. And here we also have to recall that K is equal to 1 over 4 pi epsilon naught. If we substitute that in, it reveals that the electric field around any of these situations is going to be given by KQ total over the radius squared. And that's the same whether it's a point charge or a uniformly distributed surface charge or a sphere of uniform density. So we determined that the electric field at this point, and at this point, and at this point will all be the same. And it's all given by the formula E equals KQ over A squared. But what if we want to find the field farther out? Let's say at this point here. Is the field going to be the same for all these cases? Let's find out by creating a new Gaussian sphere. Gaussian sphere is just an imaginary boundary of a surface through which field flows. Let's say that the radius of our new Gaussian sphere is r. The question is, what would change in our calculations? Well, the charge enclosed by that larger sphere is still Q total, so that hasn't changed. But what has changed? The area of our sphere has changed. In this case, we have a new area. It's given by 4 pi r squared. But our charge that's enclosed by that surface area is still the same. It's still Q total. So when we go to calculate Gauss's law, this is our setup. We replace the electric flux with E times A. This shows us that the field strength that we get here is going to be the same for a sphere of uniform surface charge and the same for a sphere of uniform charge density. All of these will have the same formula. Keep in mind, it's only because of symmetry that this idea works. If, for example, we make a Gaussian sphere around charges that are not symmetric about the center here, then the electric field here would certainly be much larger because of the position of the charge within our boundary. It'll only hold for situations where the charges are distributed symmetrically about the center of our Gaussian sphere. Next, we'd like to know what the field is going to be like inside our objects. For that, we'll create a new Gaussian sphere.